strong Roman concrete,
fully hydraulic,
structural solid connections.
It's the
Structural engineering podcast.
Welcome to this week's episode of the Structural Engineering Podcast. My name is Max.
And I'm Zach.
And we've got a real exciting episode this week.
We're diving into Taylor Devices, a company that makes dampers for structural use on International Space Station, Tomahawk missiles. We sat down and spoke with Aaron at Taylor Devices, and we hope you guys enjoy it. Could you tell us a little bit about yourself and your background? Did you start at Taylor Devices? Kind of where have you been in your career and stuff like that?
I did my undergrad in civil engineering. I got my master's in structural engineering. I did undergrad research at Atlas in Lehigh University.
Nice.
It's advanced testing of large structural systems. And I graduated in my master's in 2010, and I've worked as a structural engineer until this last year. And working as a structural engineer, I designed hospitals and bridges for high-speed rail, and my last job was an underground subway. And so I've worked on a number of different types of building applications. But I really am just always been really interested in high-performance seismic technologies. So I joined Taylor a year ago, actually.
Nice. Looking up Taylor Devices, this is sort of a newer thing for me in buildings. I know you guys are in over 600 buildings and bridges, right?
700.
700 now. That is so cool. From my understanding, Taylor Devices sort of started in the aerospace application, is that right? Sort of landing gear in the 50s?
Yeah, actually, we actually do a lot of landing gear now. The real thing that we started out with Cold War era military technology.
Jeez.
And it was actually an engineer that was working for the government that left the government after developing a product for essentially isolation and protection of different military and aerospace applications for nuclear blast.
That's pretty cool. And we saw on your website that these sort of started to go into buildings in the 1990s, is that correct? Or a little bit before that? And it retrofitted, what were they, dampers from a Tomahawk missile or something?
Yeah, no, it's pretty amazing. So for 30, 40 years, just imagine a team of really consulting mechanical engineers fine-tuning a number of different dynamic control products in the military and aerospace industry. In the 1990s, actually Doug Taylor, the son of Paul Taylor, the founder of Taylor Devices, took over as president. And one of his ideas was to see if we could make this transition from the aerospace and military industry and use these products in civil engineering applications. And so in the 1990s, that's when we first started to move into the civil engineering industry.
And was the younger Taylor, was he a civil engineer or was he a mechanical?
Both mechanical engineers.
Okay.
Both mechanical engineers.
That's awesome.
Our president now as well is a mechanical engineer. Most of our engineers, they're all mechanical engineers. I'm me, Bob Schneider, and Craig Winters, the other international sales managers are also engineers with backgrounds in structural engineering.
Nice, the right side. That's awesome. So, to give us sort of some bounds, what would be the biggest project that you have been on and maybe the smallest feasible project that would benefit from a damper civil side?
Oh, it's a great question. So one thing that is just, it's hard to talk about Taylor Devices and not go on for 4 hours for me when somebody wants to ask me about it. We are used in so many different types of applications.
Oh, yeah.
Buildings, bridges, high-rises, all different types of buildings, whether it's a 4-story or 2-story commercial residential building, or it's a museum or a hospital. And so the biggest project that we've done has been, several hundred dampers. Mm-hmm. I'm not going to give a cost specifically, but we're talking in the millions of dollars. And then on the smaller side, in the few thousands of dollars. Really, we will sell two dampers that are provide 2
Neat.
all the way up to, the 181 Fremont in San Francisco, which is, I think, the second or third tallest high-rise in San Francisco, and those are, 32, I believe, 440 kips. So really, sizes range, and although we standardize the number of our products, really, whatever the engineer specifies, we'll work with them to provide them exactly what they need. The real custom dynamic control.
Neat. So these can get pretty small. I mean, you say pedestrian bridge, that seems like a great small application for something that's vibrating a little much.
I mean, yeah, we have very small dampers that we sell to the industrial industry that we manufacture. They're just standard catalog products that they'll use with industrial applications. And so most of the time, it's just when you're dealing with building and bridge structures, you need something a little bit bigger.
Yeah,
but
yeah.
Really, still small applications are common. One thing I would say is maybe I'm diving a little bit forward, but let me know when you want to go there. But the building code has really, really evolved over time. And so when we look at American Society of Civil Engineers, ASCE 7-16, there's a whole chapter devoted to how to design buildings with dampers in there.
Yeah.
Chapter 18. So the specifications for how to design with them, how to analyze structures, but not just that, but how to test them. And the tests that need to be done to essentially validate a manufacturer's product, and then also the tests that need to be performed on every single project.
Yeah, that is awesome. Yeah, we were reading into that a little bit. Generally, how does a damper work? Kind of set the stage for what these are.
Yeah, absolutely. So a damper is just like, shocking a car. It reduces vibrations. It's a velocity-dependent device. It has no stiffness, and a force that is reactionary is all dependent upon the velocity of the stroke. And what it essentially happens is that dynamic problems occur because of built-up kinetic energy. And we all know kinetic energy is different than the strain energy in a building. And so if we want to reduce kinetic energy, we damp it.
Yeah.
And so the other industries, cars, and mechanical engineering, we've been using these for years and years and years. And it's really the buildings industry or the civil engineering industry where adding something to not just make the structure stronger, but to actually reduce the vibrations on the structure happen through the device itself.
Awesome.
So I guess right before we dive into kind of the design phase, and at what point do you guys get involved with the project?
If a structural engineer is familiar with designing with fluid viscous dampers, most of the time they could just design them, right? They could do their analysis, they have an understanding of what the capabilities of manufacturers are, and they would put them on their drawings and specify the properties. And when it goes out to bid, the contractor would, contact our company and essentially ask us for a quote. But that's not always the case. It's still a technology that's being adopted by the industry. And so you have guys like myself, we have our other sales managers, Bob Schneider, Chris Winters, that are working with customers at the earliest phases of the project to help them understand how damping can work. And so I'll work with them to support them, to give them design tools that are following building code guidelines, anything really that they need help with.
Yeah. And when you said the damper can be is basically sized in a force, you might have a 7 kip damper, like you said. Is that the maximum load that can be transferred through the damper? Since obviously the force is velocity dependent. That's sort of the capacity of these?
Yeah, it's a good question, because a lot of times people want to know, how do I get this value or how do I get that value? From a cost and material standpoint, in terms of specifying a product, the force is equal to the damping coefficient times the velocity. There's an exponent that we can put on the velocity, but let's ignore that for now. You are going to have a max velocity that your damper is going to experience based on the behavior of your structural system. And so you adding a certain amount of C value to each of the dampers is really you're just defining what that force-velocity relationship is. What force do you get based on at what velocity your building is moving at, or the stroke of the damper at what velocity. And so a lot of times I just want to get to some numbers that are more common to building applications, 55 kip, 110 kip,
Yeah.
330 kip. These are some real dampers that we're typically working with on for example, a seismic application for a building. And so it's really that's going to control the size of this device, which controls the essentially product that you get. And then also the stroke, which is essentially how much does the damper have to move from center line in each direction without bottoming out.
When we're talking pretty stiff buildings as far as retrofits go, what stroke is sort of required to get, a meaningful reaction out of this, a meaningful damping force?
It's actually, it's funny how easy it is to think about this. What's the story height? 12 feet, right? And then what's the allowable drift ratio for a story?
2%.
Building code under designers, 2%?
2%.
2%, right? And so 144 times 2%, right?
Yeah.
Is about 3 inches, so plus or minus 3 inches. And that's if it takes all the story drift. If it's at an angle, let's say a 45-degree angle, you're just going to get 0.7 of that.
Yep.
So you're going to get plus or minus essentially 2.5 inches.
So you got some movement no matter what.
Yeah.
Kind of sticking with that retrofit sort of thing.
Yeah.
The analysis is done entirely by the EOR. Is there sort of support provided by Taylor?
Yeah, obviously the ownership of the design is going to be from the structural engineer of record for the project. We will stamp our drawings if required for the devices themselves, because they are an element that's being, a part of the structural system. But throughout the project, I would provide a lot of structural engineering support to understand the process. I work with so many projects on a daily to weekly basis that you kind of get to be more of an expert along the lines of every single little code requirement.
Oh, yeah, I'm sure. Have you found sort of substantial cost savings as far as the size of a seismic resisting system when you're using a damper?
So when you talk with the person that matters, the owner of the building, you have different types of clients, and so you generally can look at 2 or 3 different things. The first thing that they're going to want to look at when they're designing a building or building a building really in their mind is cost per square foot. And so cost per square foot, if you look at a brace frame or a concrete shear wall or a moment frame with dampers, then you're looking at flexibility, right? Well, I don't want to have some bays are open or some bays are, I can't put a wall here, or I can't put a brace frame here. I want to go steel, I want to go concrete. What do the foundations look like? And so I'm super real. I could give you the spiel. It does reduce cost comparative to other systems in certain situations. And so it's always on a case-by-case basis that you want to look at something. But in general, designing a moment frame structure with supplemental damping is going to have much, much lower base shear than any other system that can be designed for that exact same building. And with much, much lower base shear, you have much less demands on the foundations. The foundations can be smaller. And then you're also going to have the options for more open systems where maybe you don't have dampers on every floor, and so you can keep it open for architects. And then you also are going to have better performance. And this is the second thing is, we look at cost per square foot of the building, but then if we start to talk about, post-earthquake performance, we enter a whole nother realm of what the impacts are and the cost benefits to the owners are. Are they lowering their insurance premiums for earthquake insurance? Just the general cost of damage to the building after the earthquake, significantly less.
And that's kind of more driving into performance-based seismic design, is that correct?
Exactly, yeah. You start to use things like FEMA P58 to evaluate the building's performance after the earthquake.
Neat. So if you're sort of, pitching to a client, you might use the resiliency argument, like you're saying, post-earthquake, that this is going to work much longer much better in the long term post-event.
Yeah, resiliency and sustainability, I think. I mean, we put so much time and effort these days into making buildings, LEED certified and sustainable. But how sustainable is it when you got to rebuild the building after the earthquake? You know what I mean?
Yeah,
So sometimes
not so much.
the additional cost, and I'm serious, we're talking $2-3 per square foot for the total cost of dampers for most seismic applications for buildings.
Yeah.
When buildings are ranging on the range of $300, $600 to $800 per square foot.
Yeah.
It's
To be 0.5%.
very small amount of additional cost to protect a building during an earthquake.
Absolutely. So I saw, reading through some of the literature on your website, that a damping system, and I don't think I understood this entirely, can be sized as an R of 8 system. Do you sell systems that are independent of a brace frame or moment frame, or do they work in tandem and can bring up the R value?
No, it's an interesting discussion. Essentially, when you are designing a structure and you're thinking of it the same way that you would think of any other structure, where you need to place a primary seismic force resisting system in that building. And it so happens that the most complementary primary seismic force resisting system is a moment frame. And so if you're designing a building and first you select where are my moment frames going to be. And most of the times when you design a structure with moment frames, it's a drift controlled structure.
Yeah.
So although you could design the moment frame for R is equal to 8, more often the R is actually equal to 4, because the building has to be twice as stiff to meet those 2% drift ratios.
Yeah.
However, if you design with dampers, the requirements is that you design the moment frame to be strength-based. So essentially, it has to be designed for R is equal to 8. There's even a 25% reduction on that. So 8 divided by essentially 0.75 will get you 10.67. So the moment frame could be as weak as a moment frame of R is equal to 10.67. And then you add the dampers to meet the drift limitation. So you take a moment frame that would have like 4 or 5% drift, but by adding the dampers, you reduce drifts to the permitted allowable.
And yes, a moment frame is the most complementary system because of the drift, do you think? Or is there some other reasons there? Because it's flexible, I guess?
Yeah, it's just the math behind it. Essentially, the energy that is dissipated in a damping device is, in a hysteresis loop, is force versus displacement during cycle of loading. If the displacement is larger, then the energy dissipated is larger under a smaller force.
Yeah.
If displacements are smaller, let's say a half inch, then to get the same energy dissipation, the forces go up. So the forces have to be higher. So it's just the math behind, hey, if I generally have a structure that has 1 to 1.5% drift, it's still a efficient design to damp that structure to all the way down to 0.75% drift from a 1.5% drift.
Nice. Okay. Looking online and dampers, kind of the only negative that I ever saw, some arguments, people were talking about service life, and you definitely address it in the website. Is there a concern or any maintenance requirements for these?
We don't think there are.
Yeah.
I mean, the requirements are that they be inspected maybe once every 2 years or something like that.
Okay.
We've had dampers on Millennium Bridge in London for over 20 years now that are actually cycling constantly because of the pedestrian vibration. They asked us to take them off to test them a couple years back, and we tested them, and they had the exact same performance as when we tested them when we put them in 20 years ago.
Awesome.
So from a standpoint of lifetime and cycle, we do have different types of dampers for different types of applications, and so you want to make sure that you specify the right type of damper for your specific application. Wind applications or pedestrian applications where the dampers are continuously cycling. There's obviously a certain amount of wear and tear on a seal versus a seismic application where maybe you're getting millions and millions of cycles, but not billions and billions like you would get with wind vibration or pedestrian vibration. So we have different dampers for different applications.
Kind of talked before, this is, a really good application in seismic region. What about high wind regions, and what are you seeing these being used for kind of the wind loading?
There's a number of applications for wind vibrations as well. We had what's called a toggle frame that was adopted, I don't know how many years ago that was, at least 10 years ago. And since then, we've also use some mega braces with dampers in there. We have outriggers that have dampers in them.
Nice.
Just for example, so when does wind vibrations control a structural design? Most of the time it's in tall buildings.
Right.
So the reason that it's in tall buildings is because when wind vibration becomes a dynamic issue. If you just have a steady wind load on a 2-story house, right? Most of the time you're not having a vibration issue. It's just the full pressure on the building. And that's not dependent upon necessarily velocity. There's no dynamic movement back and forth. But when you have tall buildings, the wind actually causes a vibration in the building. And so when you cause a vibration, the amplitude of the response of the building can be magnified when you have taller buildings. So that's when introducing damping is really, really efficient and really, really helpful.
Yeah. Do they have to be tuned to a specific frequency or a specific velocity? And then if that's the case, how do they perform out of that zone?
No, it's pretty good question as well. So a tune mass damper is actually essentially a mass with a spring and a damper that's placed in a specific location of a tower. And what it does is it shifts the fundamental period of the building.
Yeah.
And when you shift the fundamental period of the building, you're shifting it away from the peak of a wind response spectra. However, if for some reason the wind vibration ended up having the wind response spectra was shifted, which obviously they've done the studies and it's not, it would still be amplified, and that tune mass damper would move in conjunction with the building. That's why we often recommend what's called just strictly proportional damping. And when you have proportional damping, you're lowering the entire response under all modes of vibration. The 255, I want to say, West 5th Street, I could be totally off there, 255 West 55th Street in New York, is also a tower that has an outrigger with dampers in it. And so essentially they have a steel core, and then at some point in the building, you have a hat truss that trusses out to the exterior columns.
Right.
But then instead of connecting to the columns with a brace, you have a damper. And so when the building is moving back and forth, it's rocking the dampers vertically as well as horizontally, which damps out the vibrations on that building.
Oh, cool. That's a pretty neat system.
Yeah, we've been researching some outrigger systems, and that's fairly cool. We'll have to definitely dig in deeper with putting dampers there. They put up that big tower in California with they use BRBs as the outriggers. I could totally see how something like this would work really well in that system.
Yeah, and that's the problem too with earthquake events is that when you put a device like a BRB in there, you have overstrength forces. So even though that BRB is really effective in some range of loading, the demands on the structure are much higher because of the capacity of them, whereas they add stiffness to the structure. But what damping does is it adds no stiffness to the structure, but it reduces vibrations. So we found that dampers can be extremely useful in outrigger systems over other types of devices. Buckling restraint brace would yield, and it would be damaged permanently deformed. Whereas a damper is strictly velocity dependent. There is no yielding. They're designed to remain elastic during an earthquake event.
Yeah.
So just understanding the difference in what you're getting out of a product that never needs to be replaced after an earthquake.
Neat. More or less nonsense. Does it bother you when people say dampening versus damping?
You know what? It's not one of my pet peeves. I got a couple pet peeves.
Really?
That's not.
Oh man.
man.
That's Max's pet peeve.
I'm not even in this, and I tell anyone in the office we're not getting this thing wet. We're damping it, not making it dampened.
I guess.
I'll tell you one of my pet peeves, Dan, because you always have your pet peeves, right? When
Yeah.
people ask you, it is some devices can provide more damping than other devices, and that doesn't really make sense. I with all due respect to everybody, and it just, a damping is damping. It provides a relationship between force and velocity of a device.
Yeah.
So it's really about how you use them, and that's what provides damping.
Awesome.
Very cool.
Here we are.
I'm with you. It's such a cool system. I feel like
Oh, yeah.
I could really geek out on it. I would love the opportunity to work on to apply it to a project at some point. I don't know how to
Absolutely.
make that happen, but put one somewhere. Do you have any in your house?
Yeah, we do have a product that we've developed for houses as well. I didn't go there.
Oh, no way.
Another hour long.
Yeah.
But and they have been put in houses.
That is
so
cool.
yes, they can be.
All right, I'm getting one. Cool. Well, thank you very much, Aaron. We really appreciate you talking with us and telling us all about this stuff. So, thank you very much.
Excellent. Have a wonderful day, guys.
Well, thank you guys for joining us. I hope you really enjoyed that. We had a great time talking with Aaron.
We'd really like to thank him and Taylor Devices for giving us the opportunity to understand more of their system, and kind of, it allowed us to dive a little bit into ASC 7 and understand damping system.
So like usual, reach out to us, email, Instagram, Facebook, and if you have any questions, maybe we could forward those to Aaron. We'll see if he's interested in fielding those. If not, maybe we can answer them ourselves.
Have a good rest of your week.